So great. Welcome everyone to another week's intercontinental seminar on gravity and cosmology. This Wednesday, we have the pleasure to host here Adrià Gómez-Valent, whom I met, I don't know, we discussed 9 years ago in Napoli while we both were doing our PhDs. Since then, Adrià finished his PhD with Joan Solà at the University of Barcelona. Then he moved to Heidelberg as a postdoc, working with Luca Mendola, and then to Rome. And right now he's a La Caixa fellow at the University of Barcelona. And today he will talk us about insights from Angular and Anisotropic BAO data on the Hubble tension. And feel free to interrupt him whenever you want for questions. Andrea, thanks a lot. The floor is yours.
Okay, thanks a lot, Kostas, for the introduction and also for your very kind invitation. It's a great pleasure for me to have the opportunity of, talking about my work in this very nice series of seminars on cosmology and gravity. Yes, I guess all of you know what the Hubble tension is at this point, but let me remind you that it is a tension between local distance ladder measurements carried out by the SCHUS collaboration, which find values of about 73 kilometers per second per megaparsec with an uncertainty of about 1.4%. And the model-dependent estimates obtained from CMB observations in the context of lambda CDM model, okay, which in these measurements, a value of 67.5 more or less, it is found, and the tension is quite high. It's reaching the 5 sigma level, and it's even worse depending on the data set that you consider, right? So many people has tried to alleviate the Hubble tension using new physics, let's say, both in the early epochs before the recombination era and also at late times. And it's extremely difficult to reconcile observations with theory, okay? It's possible to produce values of about 71, 72 kilometers per second per megaparsec, but this usually creates other tensions in other data sectors. So given this situation, it's natural, let's say, to ask ourselves if there are tensions or not tensions, if there are systematics affecting either SCHUS measurement or other important data sectors like BAO, for instance. And this is actually the topic of my presentation. I will talk about the possibility of having some systematics in the BAO data. Okay. So in the first part of my talk, I will focus on reviewing the importance of BAO measurements in building the inverse distance ladder. I will tell you that from the very same or very similar parent catalogs of galaxies, applying different statistical techniques, one can obtain the so-called 2D or angular BAO data, and also anisotropic or 3D BAO data. And it turns out that these two BAO data sets are in tension. Okay, we will quantify this tension in a model-independent way, and also independently from the main calibrators of the inverse and direct distance ladders. And of course, this tension might reflect somehow in the lane time phenomenology that is required to solve the Hubble tension, okay? Because BAO is playing a fundamental role in the discussion. So we will review also quite model independently what are the features of the models that we require to alleviate the H0 tension at late times. Okay, and in the last part of my talk, I will tell you about one concrete model that I've developed with Joan Solà at the University of Barcelona in the last year. This is the so-called wXCDM model, and I will tell you about the phenomenological performance of this, let's let's say, theoretical framework in the context of the 2D and 3D BAO data. So let's start reviewing the meaning of the inverse distance ladder. So you know that BAO data is usually compressed in terms of these observables. This ratio is the angular diameter distance to some given redshift divided by the comoving sound horizon at the baryon drag epoch. One can also measure the radial BAO signal. Then one can extract this product, RD multiplied by the Hubble function at some redshift. And if there is no enough statistics both in the radial and angular components, one has access to this dilation scale, which is a combination of the radial and angular information. Okay. Of course, if we want to obtain late time information, we need to somehow remove the contribution of this RD. This is usually done by assuming a standard pre-recombination physics. This assumption, together with the use of CMB data, leads to this measurement of the comoving sound horizon, okay, which can be combined with this data by using it as a prior, and then one can obtain dA, dB, and H at late times at low redshift, low redshift equal to 2 typically. And combining this information with model-independent reconstruction techniques, one can reconstruct H of Z and obtain an extrapolated value for H naught. Okay. By using anisotropic BAO data, as it is usually done in the literature, one obtains typically low values of H naught in full agreement with Planck under the assumption of lambda CDM and in strong tension with shoes. But we will see that with 2D BAO, the situation is quite different. So in the first part of my talk, we will quantify the tension between these two datasets, the 3D and 2D BAO data. This is work done in collaboration with my PhD student, Adrià, and also with Professor Marina Villacho, and has been published in this Physics Letters B paper. So let's review what are the anisotropic and 3D and 2D data, BAO data. So you know that in order to obtain a tracer mapping position space, we need to convert redshift and angles, that is the observables, into cosmological distances. But of course, we don't know which is the true cosmological model ruling the expansion of the universe. So what galaxy surveys usually do is to employ a fiducial model, right? They typically use lambda CDM with some fixed parameters. Moreover, they used to employ a template function for the correlation function, which also introduces new parameters that are usually fixed. Okay, these facts might introduce some model dependencies in the anisotropic BAO measurements. And as it was noted by Anselmi and collaborators, these model dependencies might induce an underestimation of the compressed BAO information by a factor of 2, which is not a small amount. Okay, on the other hand, there is also the possibility of extracting BAO information from the catalogs without performing this translation of redshifts into distances. Okay, this is done in this in the so-called angular or 2D analysis. This methodology was proposed by Ariel Sanchez a few years ago, and the method consists basically in building shells in redshift and then computing the 2-point correlation function in angular space. Okay, of course there can be projection effects, which are usually corrected using MOX. And this method is claimed to be more model independent, okay, because you don't have to assume a fiducial cosmology. So this plot summarizes the state-of-the-art data on 2D and 3D measurements. This theta of Z is just the inverse of this quantity. So it's RD divided by the angular diameter distance to a particular redshift. And you can see here that in red and purple, I am showing the 3D measurements. The black curve is the best fit lambda CDM extracted from the CMD analysis by Planck. And you can see that there is almost a perfect agreement between these angular measurements extracted from 3D, from BOSS and also from DESI. Okay, these are the DESI data from the data release 1. Okay. In contrast, 2D BAO data shows a clear degree of tension. All the central values of these points fall above the lambda CDM curve. Okay, so this is already telling us that there is a tension between these two BAO data sets. And this tension cannot be produced by the raw data from which we derive the compressed information, because they are using similar or sometimes even the same catalogs of tracers. Okay, so this tension is due to the methodology that the various groups apply to infer this compressed information. So this tension was already noticed in 2020 by David Camarena and Valerio Marra in this paper. But here we want to quantify the tension in a model-independent way, okay, and also independently from the main calibrators of the distance ladders. Okay, and this is important because we don't want to mix the Hubble tension with the quantification of the tension between these two BAO datasets. So these are the 2D BAO measurements extracted mainly from SSDS catalogs and also from BOSS and DES. And on the other hand, we also have 3D BAO measurements. We use separately measurements from BOSS and EBOS and those from DESI, okay, because there is some overlap in the catalogs in order not to do double counting. Just to avoid double counting issues, we don't mix these two data sets. So we will analyze the tension between 3D BAO from BOSS and 2D and DESI 3D BAO and 2D. Okay. How can we do that in a model-independent way? So this, we will use only the angular component of the BAO measurements. So data on theta as a function of Z. You can see here that this quantity depends both on a calibrator, which in the inverse distance ladder is the zone horizon, and the measurement of dm. But of course, the complexity of this quantification is that, of course, we have 2D BAO data at different redshifts from those in the 3D BAO list. Okay, so we need to interpolate between these two redshifts somehow, and we do that using supernovae as redshift interpolators. Okay, I will explain now how we do that. So supernovae, remember that it also depends on the calibration of the absolute magnitude. Okay, so this is the calibrator of the direct distance ladder. We have the measurements on the apparent magnitudes, and we have the luminosity distances. So if we assume the validity of the Etherington relation, okay, this relation, this formula holds. Okay, the Etherington relation is valid if photons follow null geodesics, if we have a metric theory of gravity, and also if photons are conserved. That is, if we don't lose photons in the travel from the source towards us. Okay, we will check explicitly in the following slide that in the light of current data, Etherington relation holds. But let me explain that how the method works, how the quantification of the method works, assuming that this relation is valid. So we can express this product of calibrators, RV and M, as a function of the apparent magnitude and theta, which are our observables. Now, if we are able to reconstruct M of Z, the apparent magnitude of supernovae as a function of redshift, applying, for instance, Gaussian processes, we can estimate this quantity at all the BAO redshifts. And then we can use the resulting measurement on RD multiplied by 10 to the m fifth to quantify the tension between the BAO obtained from Angular and Anisotropic analysis. Very good. So first of all, we need to prove that the Etherington relation works well according to the current data. So instead of forcing the DL to be equal to the denominator, we allow this ratio to be different from 1. So we just say that this is a function of the redshift in general. Again, we can substitute the luminosity distance in terms of the apparent magnitude and the absolute magnitude of the supernovae. And we can substitute the angular diameter distance by the observable theta and the sun horizon RD. Okay, but this ratio again depends on how we calibrate the distance ladders, and we want to avoid that. So in order to remove the contribution of the absolute magnitude and RD, we just divide eta at 2 different redshifts, and we obtain this quantity. This quantity allows us to assess if the Etherington relation is or not fulfilled between redshift set I and redshift set J. Okay, so we can build this this function in terms of piecewise. It's a piecewise function essentially, and we can constrain it. These are the results that we find using Pantheon plus supernovae in the left and supernovae from the Dark Energy Survey year 5 on the right. Okay, and using 3D BOS in the first row, 3D DESI in the second row, and 2D BAO in the third row. And you can see that the departures from the standard case, eta equal to 1, are negligible. So they are at most of about 1 sigma, 1.2 sigma. Okay, so we do not find, using this model independent and calibrator independent method, any hint in favor of a violation of the Etherington or distance duality relation. So we are legitimated to apply this relation and proceed as I've explained before in order to quantify in order to measure this product of calibrators. And these are the results. Let's focus on this plot first. So this plot is obtained using the supernova from Pantheon Plus as interpolators. These are the individual measurements of the product of calibrators using the 2D BAO data at each 2D BAO data point. And this is the mean value, let's say. And we can do the same exercise with 3D BOS and 3D DESI, and we find that there is a discrepancy between these 2 data sets, as we have already seen before. But now we can quantify it in a more precise way. We estimate this tension to be of about 2.5 sigma, and when we replace the supernova from Pantheon Plus with the supernova from DES year 5, this tension grows to 4.6 sigma. Okay, so as you can see here, the tension is not small. Now, in view of the aforementioned tension in the BAO data sector, we can ask ourselves, what is the late time phenomenology required to solve the Hubble tension using 2D and 3D BAO? Okay, and this is work that again I've carried out in collaboration with Adrià, Favale, Marina Villaccio, and in this case we had also the pleasure to collaborate with Professor Anjan Sen. So we want to focus on late time solutions to the Hubble tension. You know, the peak, the location, the multiple of the first peak of the CMB temperature power spectrum is measured very precisely at 0.01% precision by Planck. What is the difference between late and early time solutions to the Hubble tension? In early time solutions, we basically modify the sun horizon at the decoupling time. So we can inject, for instance, some energy in order to increase the value of H before recombination. And this forces us to also lower the value of the angular diameter distance, which is a quantity that depends on late time physics. Okay, so in this way we manage to increase the value of h at low redshifts, in particular h naught. Okay, but in late time solutions we are assuming that physics before the decoupling of CMB photons is a standard. So R star, the sound horizon at the decoupling time takes the same value as in the standard lambda CDM model. And of course, in order to explain the very precise measurement of theta star, we have to keep also the denominator as in the standard model. So we need to modify the shape of the Hubble function in such a way that we manage to increase the value of h naught and keep the value of this integral as in the standard model. So we need to compensate such an increase at low redshifts with a decrease of h at high redshifts. So the data that we have used in this analysis is, of course, the shows prior on h naught. Okay, we have used some CMB priors obtained from Planck 2018 under the sanction of lambda CDM. Okay, we use a measurement of the angular diameter distance to the last scattering surface, the sound horizon at the baryon drag epoch, and a prior also on omega m tilde and h naught tilde. I will explain in a second what these parameters are. And of course, here we are considering also all the correlations existing between these parameters. And then we also use 3D and 2D BAO data separately because we want to understand what are the implications of using these two BAO data sets in a non-conjoined way, let's say. So this plot is very similar to the one I've shown before, but now I'm showing directly the angular diameter distance. Okay, once we have calibrated it with the standard value of RD. And here you can see again that there is a mismatch between 2D BAO and the standard model, which is not found in the presence of 3D BAO. Okay, for 3D BAO we also have radial contribution. So we have measurements on h offset. You can see here that they agree pretty well with lambda CDM, and also we have some measurements on the dilation scale. And in particular, you can see here a point that is very precisely measured. Okay, and we can understand few things just by looking at these plots. Okay, so 3D BAO data only gives margin to modifications of h offset at redshifts lower than this one. Okay, because this is the lowest 3D BAO redshift that we have in our data list. Okay, so whatever we do in order to explain the Hubble tension has to happen below redshift 0.15, 0.2 at most. Okay, this is one conclusion that we can extract by just looking at these plots. For 2D BAO, the situation is quite different. We need to introduce new physics at higher redshifts because we need to explain these anomalous values that I'm showing here, okay, which are close to redshift 0.8. So the fitting function that we used in this analysis is very simple. So we assume the validity of the standard model from redshift set max. Okay. Notice that here there are these two parameters, h naught tilde and omega m tilde, which are constrained using lambda CDM Planck prior. Okay, this is normal. This is a natural thing to do because we want to keep a standard pro-recombination physics. And then below this redshift set max, we have some distortion, some departure from the lambda CDM shape that we parameterize in terms of these two parabolae, okay, which depend on 6 parameters. In practice, we don't have 6 free parameters because we have some boundary conditions we force, for instance, delta H1 and delta H2 to be equal at the pivot redshift set P and also the first derivative. So at the end of the day, we have these fitting parameters, omega m tilde, H naught tilde, that, as I've said before, are essentially constrained by the Planck prior. We have H naught, which is the real value, the true value of H naught of H at present, which is constrained essentially by the prior coming from shoes. Then we have the pivot redshift set P, at which we impose the boundary condition, and then we have the departure of H from the standard model at this pivot redshift. Okay, and in principle we would also have set max, but we have checked that modifying set max, fixing it to 1, to 2, to 4 does not change the results at all. Okay, you will see that in a moment. And the methodology is very simple. We just fit this triad of data, this shoes plus Planck plus 3D BAO data, or shoes plus Planck plus 2D BAO. So the only thing that changes in one case and the other is the replacement of 3D BAO by 2D BAO. Okay. Then we perform a Monte Carlo using this data in order to see what are the preferred shapes of H of Z. And then we use our Markov chains to reconstruct the shape of M, the absolute magnitude of supernova, which in this analysis we don't assume that is a constant from the very beginning. We want to check if this assumption is true or not. Okay, we just want to ask the data what is the preferred shape for M of Z. So what we do is essentially we reconstruct the apparent magnitude of supernova using Gaussian processes. We produce random samples from these Gaussian processes, and we combine these samples with our samples of H of Z extracted from this analysis. And this is used to reconstruct M, the absolute magnitude of supernovae. So let's see what are the results. Using 3D BAO data, we find exactly what we expected. Okay, so there can be no modification or no strong departure from lambda CDM at redshift larger than 0.2. And then we have a violation of the null energy condition below that redshift. This means that we have to demand H dot to be positive. So we have a kind of phantom-like effective dark energy behavior below redshift 0.2, 0.1. The data that we are using cannot be used to set a minimum redshift at which this transition happens. Okay, so we can just put an upper bound. But what we find is that it is not sufficient to have this phantom behavior at the level of the Hubble function, but we also need a sharp transition in the absolute magnitude. Okay, so these two transitions must happen together. Okay, notice that at large redshifts, our reconstructions of MFZ are fully compatible with the, let's say, lambda CDM preferred value, which is minus 19.4. And then below redshift 0.2, we have to produce this increase to reach the value of M that is measured by the Schurz collaboration from the analysis of the first and second ranks of the distance ladder. So we can do the following exercise as well. We can say, okay, what is the preferred effective dark energy density? Okay, if we do that, these are just random curves selected, taken from the Markov chain. So you can see that there is this phantom behavior that I was talking about before, below redshift 0.2. Okay, and this is regardless of the value of Z max that we impose in our analysis. Now here we have just selected the curves that with a transition happening around 0.1 in order to visualize better what is the typical behavior of these transitions. You can see also that the acceleration parameter due to this aggressive increase in H, this manifests in a lower value of the deceleration parameter. This means that the universe is more accelerated in this scenario. Our results are fully compatible with those presented before in previous studies by Alestas, Kazantzidis, Leandros Perivaropoulos. and also Lavinia Heisenberg and collaborators. But here we remark that it is necessary in order to have a, let's say, efficient solution to the Hubble tension at low redshifts, to have a joint transition both in H and M. Okay, and this is important. Of course, if this is just a phenomenological study. If we discuss about the naturalness of these solutions, maybe they are not very natural. No, it seems that they introduce a new coincidence problem. So we should ask ourselves, okay, why is this joint transition happening all together simultaneously? Also, the transition in M seems to involve scales, local scales, while the transition in H involves local, let's say, more cosmological scales. No, so it's not natural to explain this joint transition happening both in M and H, and this is why people has explored other possibilities like early dark energy, early modified gravity, or modifications in the pre-recombination physics. As you can see here, the situation when you consider 2D BAO data is quite different. So to begin with, we can see that the transition happening in the Hubble function is much smoother. Okay, so we do not require here positive values of the first derivative of H with respect to the cosmic time. And the values of M that we obtain are compatible with this Shaw's measurement in all the redshift range. Okay, so there is no clear hint of a transition in M in this case. So we can repeat the exercise in order to understand what is the typical shape of the dark energy density. And we can see here that regardless of the value of Z max that we impose in our analysis, we find negative values of the dark energy density at redshifts larger than 2. Okay, so negative values of raw dark energy means values of delta that are below -1. Okay, and this happens in the same redshift range, both with Z max equal to 4 and Z max equal to 7. So this seems to be a robust result. And this is another way of showing that the transition has to happen at very different redshifts if you use 3D BAO or 2D BAO. Okay. So now that we have analyzed what are the phenomenological conditions that we need to fulfill in order to solve or alleviate the Hubble tension in the context of 2D and 3D BAO analysis, I would like to discuss the wXCDM model that I've developed with Professor Joan Solà at the University of Barcelona in these two papers, this Astrophysical Journal and Physics Letters V. So at the phenomenological level, the model is pretty simple. We have two components, Y and X. Y enters at redshift lower than the transition redshift that we call ZT. It has an equation of a state parameter that is constant and is close to -1. Okay, but we will see what is the preferred value of the equation of a state in the fitting analysis. I will show it later on. And of course, as usual, dark energy, raw dark energy is positive and the pressure is negative. But on top of this component, we also consider another component that we call X that enters at larger redshifts larger than the transition redshift. We keep the equation of a state parameter to be close to -1, but in this case, we consider negative contribution to the energy density and positive pressure. Okay, so we have called that, well, actually this term phantom matter was coined in this paper of 2006. We call it phantom matter because the equation of a state is close to -1 and can be lower than -1. This is why we call it phantom. But this component, the X component, obeys the strong energy condition. Okay, so as ordinary matter, let's say. No? And this is why we don't call it dark energy. We call it matter. In the rho versus P diagram, phantom matter lives in this triangle here. Okay, you can see that even though wx can be lower than -1, it is very different component from phantom dark energy. Phantom dark energy lives here, quintessence lives here, and phantom matter lives in this triangle. So,
But
of
Adrià,
course,
sorry,
yes,
I have a question. So
yes, please.
yeah, I'm not familiar at all with this model, so I'm just asking. Yeah. So wouldn't this preference, let's say, for the phantom matter behavior at high redshift introduce tensions with early universe observables, such as the CMB or BBN?
Yeah, the thing is that the values of wx that we find in the fitting analysis are very close to -1, and at sufficiently large redshifts, this phantom matter component gets diluted versus matter.
I see.
Yes,
Okay.
yes,
Thanks.
but nevertheless, it can have a huge impact on the observables, because, for instance, having negative dark energy density in the past allows you to compensate the increase of age at low redshifts. Okay, this on the one hand, this is at the background level. At the perturbations level, it can also have a huge impact. Why? Let's analyze the equation for the matter density contrast. Okay, so this is the equation that applies when the Y component, the one behaving as ordinary dark energy. So you can see here that as ordinary dark energy has positive dark energy and a negative equation of a state parameter, the friction term will increase and the Poisson term decreases. So at the end of the day, dark energy allows you to decrease the clustering in the universe. Okay, yeah, dark energy speeds up the universe and makes the universe to be less clumping, let's say. But what happens with phantom matter? Phantom matter has the opposite behavior, because now the energy density associated to this component is negative, so the friction term decreases, and also the Poisson term increases. So both facts make the universe to be more clumpy. Okay, so this might have an impact, for instance, on reconciling these anomalous observations from the James Webb Space Telescope. You know that there are some very massive, anomalous, very massive galaxies that cannot be explained in the context of lambda CDM. So having this component playing a role at large redshifts could have an impact. We have not studied this yet, but this is something that could happen. Okay. So there is a link to the theory. I will not focus on that. I leave here the references just in case some of you are interested. So it is possible to generate phantom matter in the universe when we are approaching the Sitter phases. This has been proved by, for instance, Nick Mafromatos and Joan Solà in a series of papers in the context of inflation. And we are assuming that when we reach also the Sitter phase in the late universe, this might also happen. Okay. So there is a resemblance with lambda S CDM model, which is quite famous in the literature, and it's been very successful in alleviating some tensions with observations. So this model was proposed by Othura, Carson collaborators, and has been also explored by many other groups. In this model, there is a transition from an anti-de Sitter to a de Sitter phase happening at redshift set t. And the difference with our model is essentially that we allow for dynamics in the late universe. So we don't have a negative and a positive cosmological constant, but we have something that evolves with the cosmic expansion. And we will see that actually, even though we are introducing new parameters in the model, we are improving by a lot the description of the data. Okay. So even though we can penalize the use of extra parameters using Bayesian tools, at the end of the day, this model wXCDM is favored from a Bayesian perspective. So in our fitting analysis, in our first fitting analysis, we use Planck 2018 CMB polarization, temperature, and lensing, Pantheon Plus supernovae, cosmic chronometers, 2D BAO, and large-scale structure information in the form of redshift space distortions. So these are the fitting results, which show it's a comparison between lambda CDM, wXCDM, and lambda SCDM. You can see that lambda CDM, when using 2D BAO, is able to produce larger values of H0. However, this is a mid-edge. Lambda CDM cannot solve the Hubble tension even in the presence of 2D BAO. Why? Because it cannot make the absolute magnitude of supernova to be close enough to the value measured by Schuss, which is minus 19.27 plus minus 0.027. Okay. So you see here that we can produce larger values of H0, but M lies far away from the value measured by Schuss collaboration. This is not found in the context of lambda SCDM and wXCDM. Both models are able to produce large values of H0 using 2D BAO, and this is important. And they are also able to explain, let's say, large values of M in full accordance with Schuss. Okay. In both cases, the transition happens close to redshift 1.5. And we can see here, though, that we have a preference for quintessence behavior at redshifts lower than 1.5. Okay. And the preference is at the level of 3 sigma. At the level of the information criteria, you can see here that both models, lambda CDM and wXCDM, beat by a lot lambda CDM, and actually we can exclude lambda CDM from this analysis. But there are differences, right, between lambda CDM and wXCDM. We are able to increase by 17 units the deviance information criteria, and also by some units, sorry, I cannot see the value of AAC because, okay, I think that it's 10 units or so as well. And this means that we are able to improve the description of some data sets at least. So let's try to see which is the improvement. So the improvement between wXCDM and lambda CDM comes from the better description of the supernovae data. Okay, and this can be understood as follows: if you take the diagram in the omega m W plane, you can see here that lambda SCDM, since W is equal to -1 because we have a cosmological constant at late times, the lambda SCDM falls in this part. In both models, we require low values of omega m, much lower than in lambda CDM. Notice that here we have 0.27 and here we have 0.28. So in both models, we have values of omega m close to 0.26, but lambda SCDM has W equal to -1, and this makes this point to be in the 3 sigma region of Pantheon plus data. Whereas if we allow for this extra degree of freedom in the wXCDM, then we find that the point falls in the 1 sigma region. Okay, this is why we can improve the description of the supernova data. And similar things happens if you consider unit 3 data or the DES GR5 sample. Okay, of course, here the level of conflict with DES increases with lambda SCDM because we have more statistics at large redshifts. So this is another way of visualizing the 3 sigma preference of quintessence in late epochs in the context of the wXCDM. And in our most recent paper, the Physics Letters B paper, we explored what happens if we substitute Pantheon Plus by DES GR5, and of course, the situation, so the wXCDM is more favored than lambda CDM. Lambda CDM is still excluded, also the wCDM, so it's not sufficient to have, let's say, a constant equation of a state, but we need either to have some evolution of it, or we need this sharp transition as we found in these 2 models. Okay, but notice that the description of the data is the best description comes is found in this model, in wXCDM. But it's interesting, of course, not to take only the results that we obtain with 2D BAO, because we don't know actually if 3D BAO is the correct BAO dataset. Okay, so it is let's say fair also to constrain our models using 3D BAO, and this is what happens. As we found in our phenomenological analysis in part 2 of this presentation, there is no possibility of solving or alleviating minimally the Hubble tension in the context of 3D BAO. Actually, there is no late-time dark energy model able to do that. You have to consider also variation in M, which is not what we are analyzing here. We are considering a constant M, and this is why these models cannot alleviate the Hubble tension. But nevertheless, it's important to see that the CPL parameterization makes a good job. Okay, take into account that we are not using DESI data here, so these results were obtained using still BOS and eBOS. And actually, if you compare the central values of these two parameters that control the present value of the equation of state and its evolution, they are very similar to those provided by DESI some months later using DESI data. Okay, this means that most of the signal maybe comes from supernovae data. Okay, and we see that even though our models are not able to solve the Hubble tension, the wXCDM still makes a good job. It has a delta AC which is close to the one found in the CPL parameterization. Okay, and still we have a hint for quintessence at late epochs. Okay, so I'm going to conclude. So let me tell you what are the main take-home messages. So of course we have seen that BAO, and in particular the inverse distance data, play a very important role in the discussion of the Hubble tension. We have seen that it is possible to extract to apply different statistical techniques to extract the information from the galaxy catalogs, and the anisotropic and angular BAO data are in tension, which goes from 2.5 to 4.6 sigma, depending on the supernovae data that you consider to perform the interpolation. Anisotropic BAO data requires a very low redshift departure from lambda CDM. It has to happen below redshift 0.15, and it has to be simultaneous to the transition in the absolute magnitude. Okay, angular BAO data are not in conflict with a constant M. Okay, this is in full accordance with shoes, and the dark energy density must exhibit negative values at redshift larger than 1.52. Okay, we have seen that in the context of the 2D BAO data, wXCDM solves the Hubble tension. Okay, it also produces values of the amplitude of the power spectrum fully compatible with large scale structure observations. It can improve the fitting performance of lambda SCDM, and the model also does a very good job in the presence of 3D BAO, okay, which is comparable to the CPL parameterization, although as expected it cannot solve the Hubble tension. Okay, so this is all I wanted to explain. Thank you very much for your attention, and now I will be pleased to take questions, if any. Thanks a lot.
Thank you very much, Adrià, for the very nice talk. Are there any questions from the audience? Yeah, maybe people are shy. So I wanted to ask. So I mean, yeah, about this tension between the angular and anisotropic BAO data. So you used supernova, type 1A supernova, as redshift interpolators, right? So I would,
Yes.
I mean, I'm not an expert again, but like given the fact that supernovae themselves have their own calibration dependencies, how robust is this model independent approach?
Yeah,
I mean,
this is why we opted to show the level of tension using both Pantheon and DES ER5, because we know that there are some issues. Well, there are some claims that
yeah.
the SGL5 data have some problems with the calibration and so on. And this is why we wanted to show the results with the two data sets. Nevertheless, let me tell you, and I have not maybe remarked this enough in my presentation, here in this quantification of the tension, we are only using the angular component of the 3D BAO, okay? Because we are applying a model-independent method which only allows us to use the angular part. So maybe my feeling is that this is a lower bound of the tension, even though we have
I
not
see what
checked
you're
that
saying.
because
Yeah.
we cannot apply this model-independent technique using the radial component.
Good, good. Any other questions from the audience? Well, either they understood everything or they understood nothing,
Very good.
right? Okay, let me stop the recording and maybe some people are shy. So.